Hey everyone, and welcome to our deep dive, into nuclear fusion.
Yeah.
We're going to be cracking open Edward Morse's book, Nuclear Fusion,
Oh, great.
to try to get a better understanding of this potential powerhouse, of clean energy.
Yeah.
Imagine harnessing the power of the sun right here on Earth.
It's a fascinating goal and, one that scientists have been working towards for decades now.
Yeah, and Morse really starts off strong,
Hmm.
talking about this looming energy crisis,
Right?
showing how global energy consumption is projected to just absolutely skyrocket.
Yeah.
So it's pretty clear, we need new energy sources.
Yeah.
But why is fusion, such a promising solution?
Well, unlike fossil fuels, fusion doesn't produce greenhouse gases. And compared to nuclear fission, which we use today in power plants,
Right.
fusion is inherently safer.
Oh, wow.
It produces far less radioactive waste, about 100,000 times less, according to Morse.
Wow, that's a huge difference. So
Yeah.
no risk of meltdowns like Chernobyl or Fukushima.
It's exactly. A runaway chain reaction like what happened in those disasters is impossible with fusion.
That's a huge relief.
Yeah.
But I remember hearing about two different ways to achieve fusion.
Uh-huh.
Something about magnetic bottles and lasers.
Right.
What's the difference?
You're thinking of magnetic confinement fusion, or MCF,
Mm-hmm.
and inertial confinement fusion, or ICF.
Huh?
MCF uses powerful magnetic fields to contain the superheated plasma where fusion happens.
Right.
Think of it like a magnetic bottle holding a miniature sun.
Okay, that makes sense. And what
Yeah.
about ICF?
Yeah,
Does it also use a magnetic bottle?
not quite.
Okay.
ICF uses lasers or particle beams to implode a tiny fuel pellet,
Oh, wow.
creating the extreme heat and pressure needed for fusion in a very short burst.
So like a miniature star going supernova.
Yeah.
That's incredible. So both methods are trying to create conditions similar to the sun, but on vastly different timescales.
Exactly.
Yeah.
And the timescale difference is huge. In MCF, we're trying to hold the plasma steady for seconds, while in ICF, the whole implosion happens in nanoseconds.
Wow, that's insane.
But before we get into those details,
Yeah.
let's take a step back and look at how this whole quest for fusion began.
Okay, let's rewind the clock.
Okay.
Morse mentions that it all started back in the 1930s with the discovery of nuclear reactions. What was the scientific community like back then?
It was a time of incredible breakthroughs. Scientists were unraveling the mysteries of the atom and discovering the immense energy locked within its nucleus.
And that led to the idea of harnessing this energy through both fission and fusion.
Exactly.
Wow.
Early pioneers in fusion research faced incredible challenges.
Yeah.
They were working with new technologies and grappling with the complex physics of plasma.
Right.
One of the first attempts at controlled fusion was an experiment called Zeta, which used magnetic confinement.
Zeta, that
Yeah.
sounds familiar. Didn't they use something called ohmic heating in that experiment?
Yeah,
What was that all about?
good catch. Ohmic heating, sometimes called resistive heating, involves passing a huge electrical current through the plasma to heat it up.
Okay.
It's kind of like using an electric stovetop, but on a much grander scale.
So they were essentially trying to cook up a mini sun with electricity.
Yeah,
That's amazing, but then lasers came along and changed everything, right?
got it.
Okay.
The invention of the laser in the 1960s opened up the path to ICF.
Okay.
There's a really interesting story about John Nuckolls,
Uh-huh.
a scientist at Lawrence Livermore National Laboratory.
Okay.
He had this groundbreaking idea back in 1958 about using lasers to implode a fuel target and achieve fusion,
Right.
but his work was classified for years.
Wow.
It wasn't until 1972 that his memo was finally declassified and published.
Wow. A classified fusion memo. It sounds like something out of a spy movie.
Yeah.
And Livermore seems to have played a big role in early laser fusion research.
They were on a mission.
Okay.
They started with smaller lasers and kept pushing the limits, building bigger and more powerful ones. There's some great photos in the book, like figure 1.12.
Okay.
They show these early laser systems. They name them Cyclops, Janus, Argus, Shiva. It's like a roll call of mythical creatures.
Those names are pretty epic. So what were they doing with all that laser power?
They were learning how to control these intense beams of light
Yeah.
and use them to compress and heat tiny fuel targets.
Okay.
There's a fantastic description of their 12-beam laser fusion target chamber
Yeah.
from the mid-1960s in figure 1.11.
Wow.
Imagine a room-sized chamber with 12 powerful laser beams all converging on a tiny pellet.
Yeah.
It must have been an incredible sight to see.
I can only imagine. Okay, so we've got this grand challenge,
Yeah.
creating fusion power here on Earth.
Right.
We've got two main approaches, magnetic confinement and inertial confinement.
Yeah.
And we've got this fascinating historical backdrop of scientific discovery and technological innovation.
Yeah,
But I have a feeling things are about to get a whole lot more complex.
you're right. To really understand how fusion works, we need to dive into the world of plasma physics.
It's a wild and fascinating realm where things behave very differently from the everyday world we're used to.
Plasma physics, bring it on. I'm ready to get into the nitty-gritty. But you know me,
Uh-huh.
I need more than just equations and abstract concepts.
Don't worry, I'll make sure to ground our exploration in the fascinating details and real-world examples that Morse provides in his book.
Great. So tell me, what exactly is plasma? I keep hearing it's the fourth state of matter, but what does that actually mean?
It's a great question. Imagine heating a gas to such extreme temperatures that the atoms themselves break apart.
Oh, wow.
The electrons are stripped away from the nuclei, leaving you with a swirling sea of charged particles.
Okay.
That's plasma. It's kind of like a supercharged lightning storm, but way hotter.
So it's like a chaotic soup of charged particles. No wonder it's so difficult to control.
Exactly.
Ah.
And this plasma is where the magic of fusion happens.
Okay.
Morse provides a helpful table in Figure 2.5 showing the different fusion reactions between light elements. Light elements, so we're not just fusing any old atoms together.
Not at all. The most promising reaction for fusion power is the deuterium-tritium, or DT reaction.
Okay.
Deuterium and tritium are both isotopes of hydrogen.
Okay.
Their nuclei readily fuse together at incredibly high temperatures, releasing tremendous energy.
Okay, the DT reaction is our star player.
Yeah.
But hold on,
Right.
I remember from high school physics that, charges repel. How do we get these positively charged nuclei to actually fuse? Wouldn't they just push each other away?
That's the biggest challenge.
Yeah.
Overcoming that electrostatic repulsion requires incredible heat on the order of millions, even tens of millions of degrees Celsius.
Millions of degrees.
Yeah.
That's mind-blowing.
It is.
But there's more to it than just heat, right?
Yeah.
Morse mentions these things called cross-sections and reactivities.
Right.
What are those all about?
Those are key to understanding how likely fusion reactions are to occur.
Okay.
The cross-section visualized in Figure 2.6
Right.
is basically a measure of the probability that two nuclei will collide and fuse.
Okay.
The reactivity takes into account both this cross-section and the speed of the particles.
Right.
Think of it like this. If you have a room full of people moving slowly, the chances of them bumping into each other are low.
Mm-hmm.
But if they're all running around, collisions become much more likely.
So higher reactivity means more fusion fireworks.
Exactly.
I'm starting to see the connection.
But there's another crucial factor, confinement.
Okay.
We need to not only heat the plasma to those extreme temperatures,
Right.
but also keep it confined long enough for those collisions and fusion reactions to happen.
Right. We can't have our mini sun just sputtering out, can we?
Right.
This is where those magnetic bottles and laser implosions come in, right?
Absolutely. And that brings us to the next fascinating aspect of fusion,
Okay.
plasma behavior.
Okay.
It turns out plasma isn't just a static hot soup of particles.
Yeah.
It's a dynamic and often unpredictable entity with its own set of quirks.
Okay, I'm picturing a wild swirling mass of charged particles constantly moving and interacting. What kind of quirks are we talking about? And I'm ready for the wild side of plasma.
Well, buckle up.
Okay.
For starters, plasma can oscillate,
Okay.
almost like a vibrating string.
Oh, wow.
It also exhibits something called Dubby shielding,
Okay.
where charged particles tend to surround themselves with a cloud of oppositely charged particles.
Dubby shielding. It sounds kind of like those magnetic fields we were talking about earlier.
You're on the right track.
Okay.
It's all about electric and magnetic fields influencing the movement of those charged particles.
Right.
But let's save those details for our next installment, where we'll really dig into the intricacies of plasma behavior and how it impacts our quest for fusion energy.
Okay, I'm hooked. Can't wait to uncover more of these plasma mysteries. Until next time.
Yeah, see you then.
Welcome back to our deep dive into nuclear fusion. Last time we were talking about the challenges of containing this superheated plasma.
Right.
But how do we even get it to those crazy high temperatures in the first place?
That's a great question. Remember, fusion requires temperatures hotter than the core of the sun.
Yeah, it's mind-blowing.
It is. Getting there takes a lot of energy and some clever techniques.
Right. We talked about ohmic heating passing a current through the plasma.
Uh-huh.
But Morse's book mentions that's not always enough.
Right.
Especially at higher temperatures. What are some of the other heating methods scientists are exploring?
There are two main approaches besides ohmic heating: neutral beam injection and radio frequency heating.
Okay.
Let's start with neutral beam injection, or NBI.
Okay.
Imagine shooting high-energy particles into the plasma to heat it up.
Okay, so it's like giving the plasma a power boost.
Yeah.
But wouldn't those particles be deflected by the magnetic fields that are supposed to contain the plasma?
That's where the neutral part comes in.
Oh,
We start with a beam of ions, which have an electric charge,
okay.
but we neutralize them by adding electrons.
Oh.
These neutral particles can then zip right through the magnetic field and into the plasma.
Ah, so they get a neutral camouflage to sneak past those magnetic defenses. Clever. But what happens once they're inside the plasma?
Once inside, they collide with the plasma particles, transferring their energy and heating things up.
Yeah.
It's kind of like a game of billiards with the neutral beam particles acting as the cue ball,
I don't know.
transferring energy to the other balls on the table.
Okay, I'm picturing those neutral beam particles ricocheting around, transferring their energy and heating up the plasma.
Right.
Makes sense. But Morse's book also mentions something about radio waves being used to heat the plasma.
Right.
That sounds pretty wild.
Is radio frequency heating, or RF heating, is a fascinating approach.
Okay.
Imagine using antennas to send radio waves into the plasma,
Right.
where they transfer their energy to the particles, heating it up. It's a bit like using a microwave oven to heat your food.
So we're essentially blasting the plasma with radio waves to get it hot enough for fusion. That's amazing.
It is.
But I imagine it takes some fine-tuning to get those radio waves to do their job properly.
Absolutely. It's all about finding the right frequency for those radio waves.
Okay.
It's like tuning your radio to find your favorite station.
Right.
You need to hit the sweet spot where the radio waves resonate with the plasma particles
Yeah.
and transfer energy efficiently.
Resonance. So we're making the plasma particles dance to the tune of those radio waves.
Yes.
That's a great way to picture it. But are there different types of RF heating?
You're
I
right.
imagine it's not a one-size-fits-all situation.
There are actually several different RF heating techniques,
Mhm.
each targeting a specific frequency or type of particle in the plasma.
Oh, wow.
For example, there's electron cyclotron resonance heating, or ECRH,
Okay.
which focuses on heating the electrons,
Uh-huh.
and ion cyclotron resonance heating,
Mm-hmm.
or ICRH, which targets the ions.
So it's like having a whole toolbox of RF heating methods, each with its own specific purpose and frequency range.
Exactly.
Yeah.
Scientists and engineers can choose the best heating method or combination of methods depending on the specific conditions of the plasma and the goals of the experiment.
That's pretty cool. It sounds like heating the plasma is a complex and carefully choreographed process.
It is.
But we've been focusing on magnetic confinement fusion.
Right.
Do these heating methods apply to inertial confinement fusion as well?
Good point. Remember, in ICF, we're using lasers or particle beams
Yeah.
to implode a tiny fuel pellet.
Right.
So the heating process is a bit different.
Yeah.
The lasers themselves provide the initial energy to heat and compress the target.
Right. We talked about those incredible lasers earlier, the ones with names like Cyclops and Shiva.
Yeah.
But I'm guessing it's not as simple as just pointing a laser at a fuel pellet and watching it go boom.
You're right. It's a very intricate process.
Okay.
When those intense laser beams hit the fuel target, they create a plasma.
Uh-huh.
And that plasma can interact with the laser light in complex ways.
Okay, so it's not just a one-way street of the laser heating the target.
Right.
What kind of interactions are we talking about?
Well, one of the challenges in ICF is something called laser plasma instabilities. These instabilities arise from the interaction between the laser light and the plasma it creates.
Right.
And they can disrupt the implosion process.
Instabilities. It seems like instability is a recurring theme in fusion, whether we're talking about magnetic confinement or inertial confinement. Why are these instabilities such a problem?
These instabilities can scatter the laser light or cause the fuel to preheat unevenly, making it harder to achieve that perfect implosion we need for fusion.
So it's like trying to build a house of cards in a windstorm.
Exactly.
Everything has to be perfectly aligned and stable for it to work.
And just as in magnetic confinement, fusion controlling these instabilities is a major focus of research in ICF.
So it's a constant battle to maintain stability and achieve those ideal conditions for fusion, whether we're using magnets or lasers. It's incredible to think about the precision and control required.
It is. But even when we get that perfect implosion, there's still the question of how the fuel behaves under those incredibly extreme conditions. Remember, we're talking about pressures and densities far beyond anything we experience in everyday life.
Okay, so now we're getting into the really extreme physics.
Okay.
What happens to matter under those kinds of pressures?
Those laser beams hitting the fuel target generate incredibly powerful shock waves.
Wow.
These shock waves are crucial for compressing and heating the fuel,
Okay.
but they also create a mind-bogglingly complex environment that's difficult to model and understand.
I'm trying to wrap my head around it. We're talking about creating conditions that are even more extreme than the center of the sun right here on Earth. It's amazing.
It is, and to understand what's happening in that tiny, ultra-dense core, scientists need to use some pretty heavy-duty physics.
Yeah.
They rely on equations that describe the behavior of matter under extreme conditions.
So we're talking about equations that go beyond the typical physics we learn in school.
Right.
What kind of concepts are involved here?
One of the key tools for understanding shock physics is something called the Rankine-Hughes equations.
Okay.
These equations describe the relationships between pressure density and velocity across a shock wave, helping scientists predict how the fuel will behave during implosion.
Okay, so we're using complex equations to model the shock waves. But there's something else, right? I remember you mentioned equations of state earlier. How do those fit into the picture?
Excellent memory. The equation of state, or EOS, is like a material's fingerprint.
Okay.
It describes how the material's pressure, temperature, and density relate to each other.
So it's like a recipe that tells us how the fuel will react under different conditions.
Exactly.
Oh.
And in the extreme conditions of an ICF implosion, those equations of state become incredibly complex.
Wow.
We're dealing with ultra-dense hot plasmas that are far from their normal states.
So it's not just about getting the fuel hot and compressed. It's
Yeah.
about understanding how the material itself behaves under those mind-bending conditions.
Precisely. Scientists need to develop sophisticated EOS models that take into account things like quantum mechanics and radiation pressure, which become significant at these extreme densities and temperatures.
Quantum mechanics and radiation pressure. Wow, this is getting pretty deep.
Yeah.
But it sounds like we're getting close to the heart of the matter, literally. How do those fusion reactions actually get triggered in an ICF implosion?
That's where it all comes together.
Okay.
As those shock waves converge towards the center of the fuel target, they create an incredibly tiny, ultra-dense, and superheated core.
Right.
And that's where the magic happens, the fusion ignition point.
Fusion ignition, it's like the spark that starts the whole process, right?
Yeah.
What happens next?
The goal is for that initial spark to trigger a self-sustaining burn wave that propagates outwards, consuming the rest of the fuel and releasing that massive amount of fusion energy.
Ah, so it's like a chain reaction.
Yeah.
One fusion reaction sets off another and another until the whole fuel target is consumed.
Exactly. It's a delicate dance of precision and timing. Achieving that perfect implosion with the right shockwave timing and the right fuel conditions is the ultimate goal of ICF research.
I'm starting to grasp the incredible complexity involved in making fusion happen. We've talked about the challenges of heating the plasma, controlling instabilities, understanding equations of state,
Yeah.
and achieving ignition.
Right.
It's mind-boggling.
It is.
But what happens after that burst of fusion energy?
Right?
Do we just start the process all over again?
That's a great question, and it leads us to the next chapter of our fusion story, where we move from the intricacies of physics to the equally challenging world of fusion technology and engineering.
Okay, I'm ready to move from the theoretical to the practical. Let's explore what it takes to actually build these incredible machines and make fusion a reality. See you next time. Welcome back to our deep dive into the world of nuclear fusion. We've explored the incredible physics behind fusion, from heating plasma to triggering those powerful reactions.
Right.
But now I'm curious about the practical side of things.
Yeah.
What does it actually take to build a fusion reactor?
That's where the real challenge begins.
Yeah.
We're talking about creating and containing conditions that are hotter than the core of the sun. It takes incredible engineering and some seriously tough materials to build a machine that can withstand those extremes.
That makes sense. We've talked about those super hot plasmas and powerful lasers. What kind of materials can handle that kind of heat and radiation?
It's one of the biggest questions in fusion research.
Yeah,
Remember those high-energy neutrons that are produced in fusion reactions?
you're right.
They can cause a lot of damage to the material surrounding the plasma. Think of it like throwing sand at a wall constantly. Over time, those tiny impacts can wear down even the strongest materials.
Wow, so it's like the reactor is under constant bombardment from those neutrons. Are there any materials that can stand up to that kind of abuse?
Researchers are always on the lookout for materials that can withstand the harsh conditions inside a fusion reactor.
Right.
They're looking for things like high melting points, good thermal conductivity, and resistance to radiation damage.
So we need materials that can take the heat conducted away and withstand those neutron attacks. Sounds like a tough combination to find.
It is. Some materials used in today's nuclear fission reactors, like stainless steel, are being considered.
Okay.
But there are also more exotic materials like tungsten and vanadium alloys, which are known for their high melting points and better resistance to neutron damage.
Tungsten and vanadium, those sound like they're straight out of a science fiction movie.
They might sound futuristic, but these materials are playing a crucial role in pushing fusion technology forward. But even with the best materials, there are other challenges to overcome.
Okay, like what?
Well, one of the big ones is tritium. It's an isotope of hydrogen that's a key ingredient in those energy-releasing fusion reactions we talked about.
Right, I remember tritium, but what's so challenging about it?
Well, tritium is radioactive, so we need to be very careful about how we handle and contain it. Plus, it's not readily available in nature, so we need to find a way to create it within the fusion reactor itself.
So we're not just using up tritium, we're also making more of it inside the reactor. How does that work?
The process is called tritium breeding.
Okay.
We use lithium, another lightweight element, to produce tritium. When lithium is hit by those high-energy neutrons we talked about earlier, it can transform into tritium. It's pretty ingenious.
That is clever. So we're essentially creating our own fuel as we go along. But how do we make sure that tritium, which is radioactive, doesn't escape into the environment?
That's a crucial concern. Tritium containment is a top priority. Fusion reactor designs include multiple layers of protection to prevent tritium from leaking out.
Okay, so it's like a high security vault for tritium.
Exactly.
Yeah.
We need to be absolutely sure that we can handle tritium safely and responsibly if we want fusion to be a viable energy source.
That makes sense. So we've got these super tough materials and a way to handle tritium. What other engineering feats are involved in building a fusion reactor?
Well, we can't forget about the magnets.
Right.
They're essential for magnetic confinement fusion, creating those powerful magnetic fields that keep the hot plasma contained.
Right. Those magnetic fields were key to the whole concept of magnetic bottles. What's so special about the magnets used in fusion reactors?
Well, we're talking about creating magnetic fields that are thousands of times stronger than the Earth's magnetic field.
Wow.
To achieve that, we use superconducting magnets.
Superconducting magnets. I remember hearing that term before, but remind me what makes them so special.
Superconductors are materials that can conduct electricity with zero resistance when they're cooled down to extremely low temperatures.
Right.
This allows us to create incredibly strong magnetic fields without losing energy to heat.
Zero resistance. That sounds amazing.
It is.
But I imagine keeping those magnets cold must be quite a challenge.
You're absolutely right. We're talking about temperatures just a few degrees above absolute zero,
Oh, wow.
which is colder than anything found naturally on Earth.
Yeah.
Maintaining those temperatures requires sophisticated cooling systems and a lot of insulation to prevent heat leaks.
So it's like we're building a giant high-tech refrigerator just for the magnets.
You could say that. But there's another challenge: radiation damage.
Uh-oh.
Remember those neutrons?
Yeah, those neutrons are always causing trouble.
They can also damage the superconducting materials in the magnets over time, reducing their performance.
So how do we protect the magnets from them?
Fusion reactor designs often include thick shielding around the magnets to absorb those neutrons and minimize the damage.
It's amazing to think about all the engineering challenges involved in building a fusion reactor. We're talking about super tough materials, tritium breeding and containment, powerful superconducting magnets, complex cooling systems, and radiation shielding.
Right.
It's a lot to juggle.
It's a truly monumental undertaking, requiring expertise from a wide range of disciplines. From physics and material science to engineering and computer modeling.
It really highlights the collaborative nature of science and engineering. But with all these complexities and challenges, is fusion power even economically feasible? I mean, can we realistically build and operate these machines on a commercial scale?
That's the billion-dollar question. The economics of fusion power is a complex and evolving topic.
Yeah.
Building a fusion power plant would require a significant upfront investment. But if we can make it work, the potential payoff is huge: clean, safe, and virtually limitless energy.
Okay, so it's a long-term investment, but one with the potential to revolutionize our energy future. What are some of the key factors that will determine the cost of fusion power?
The cost of materials, the efficiency of the fusion reactions, and the complexity of the engineering will all play a role. There are also different financing models being explored, with potential roles for government funding, private investment, and international collaborations.
It sounds like fusion power might be too big a challenge for any one country to tackle alone.
You're probably right. Fusion research has always been a global effort, bringing together the best minds from around the world to solve one of the biggest challenges facing humanity.
Clean energy. That's inspiring. But before we get too carried away with the promise of fusion, what about its environmental impact? We know it's much safer than fission, but are there any other environmental considerations?
Fusion has the potential to be a remarkably clean energy source.
Yeah.
It doesn't produce greenhouse gases or the kind of long-lived radioactive waste that fission does. But there are still some things we need to consider.
Like what?
Well, the mining and processing of the materials used in fusion reactors could have some environmental impact.
Right.
And even though fusion produces much less radioactive waste than fission, we'll still need to handle and dispose of that waste responsibly.
So it's important to consider the entire life cycle of fusion power, from the raw materials to the final waste disposal, to ensure it's truly a sustainable energy source.
Absolutely. And that's why scientists and engineers are working to optimize every aspect of fusion technology, minimizing its environmental footprint while maximizing its benefits.
Well, this deep dive into nuclear fusion has been an incredible journey. We've covered a lot of ground, from the mind-blowing physics of plasma to the complex engineering of fusion reactors, the challenges of materials and tritium, and the economic and environmental considerations. It's been fascinating.
It's a testament to human ingenuity and our drive to find solutions to some of the biggest challenges facing our planet.
It really shows how science and engineering can come together to push the boundaries of what's possible. I feel like I've gained a whole new appreciation for the complexity and the potential of fusion power.
That's the goal.
Yeah.
While fusion power might still be a few decades away from becoming a reality, the progress in recent years has been remarkable. Who knows, maybe one day, thanks to the dedication and collaboration of researchers worldwide, we'll all be powering our homes with the energy of the stars.
That's an amazing thought. Thanks for joining us on this deep dive into the world of nuclear fusion.
It's been my pleasure. And to our listeners, keep exploring, keep learning, and keep that spark of curiosity burning.